Okay. Very good. So we're going to pick up where we left off. We'll conclude easily methods of, growth today, and start into methods of, which is sort of the natural transition. Because as we go over these things, these are all areas that we look at with the eventuality of being able to control microbial growth. It's the old story. Understand how they grow, then you understand how you stop them from growing, which is where the therapeutics come in. So and today the focus point is certainly this, which you'll see very shortly. This guy, the bacterial growth curve, that you can see over there. So we'll get back to that in just a second, and let me get started here. This is kind of where we left off. Okay, I mean, this is where we looked, and there's not a whole lot. Most of the organisms, you might recall me saying at the very end, are called neutrophiles, which again is different than a neutrophil, which is the most common of all the white blood cells. But neutrophiles, roughly pH 6 to 8 is about the usual place where we see them. You do see some of these oddballs periodically. Maybe the one that affects us is Proteus. Proteus may be about the second or third most common organism for urinary tract infections in women. And it's typically a fecal contaminant, which is typically from catheters, how we see the vast majority of these in a hospital sense. Which brings us to this, and this is the idea, living in habitats that have a lot of solute, which is generally a big problem. Okay, salting and using high quantities of osmotic products have been the time-honored method of controlling microbial growth since the early days, since the old story with salt and salting meats and salting vegetables and salting fruit and everything. So if you go back, it's the old days, the derivation of the word salary. You've probably heard this before. Salary comes from salt, how they pay the Roman soldiers, and salt, worth their salt, that whole deal, salt mines, and all that good stuff. So that's the whole idea about salt. Now, there are some that have to grow in it, and some that are remarkably resistant, okay, and they don't normally reside. But the real player here, I think, among them all is Staphylococcus aureus. So Staph aureus is a very, very interesting organism because it's really a halophile. It exists on our skin. Our skin is a very salty environment. So why is it so able for not just Staph aureus, but its cousin Staphylococcus epidermidis, which is on all of our skin 100% of the time? And they are potent disease causers under the right circumstances, particularly in those individuals that have any pre-existing conditions or damage to the tissue. So it's a real annoyance. And you'll hear me say it again and again. To me, it's public enemy number one, the Staph aureus. So in the laboratory, how do we isolate it? Okay, so we use what's called selective media, and maybe you'll get to that this week in lab, maybe not, or maybe you got to it already. What selectivity in media means that you add something to the media to either retard the growth of something or favor the growth of something. And in the case of salt, it's easy because salt's easy to find, and you're going to be using agars that have about 7% salt concentration. Most famously is called MSA, mannitol salt agar. So the salt favors the growth of Staphylococcus or other halophiles. The mannitol is a sugar that Staphylococcus aureus can ferment easily, and it produces acid by fermentation. So the agar is red. They had a very, very important chemical dye called phenol red, and phenol red in the presence of acidity turns yellow. That's the beauty of lab, is we utilize dyes, and most of these dyes have different they appear differently at different pH levels. So they're pH related dyes. That's the neat thing about that. Probably the earliest one that most students saw is in the chemistry lab, when it looks like a clear liquid, and you add phenolphthalein and it magically turns pink. There's so many of those. There are neat things in chemistry experiments that you can do to impress the students. But nevertheless, this is and you'll see this all over in the laboratory. So even though many of you are not going to be utilizing the laboratory, this is kind of where it comes from, how you're able to do this. And what they do when they analyze bacteria is they'll simultaneously inoculate maybe 24 or so tiny wells with different dyes and chemicals in them, and you'll see which ones kind of turn colors or which ones have a reaction. And there's a formula, and you can identify very, very specifically what the organism is. So it's like a multi-test kind of thing. It's been around for a long time. They have. So they're always changing them, and I don't know that we use them in our lab. We probably just use individual tubes. It's a little less expensive. Nevertheless, radiation, something we're going to utilize more in therapeutics. Okay. Well, obviously, certain organisms utilize light as an energy source, but photosynthetic microbes, which is the ones that affect us, damaged by toxic oxygen products produced by contact with light. And I mean, there's some oddball ones produced carotenoids to absorb and dismantle, but the big deal is here is the ability to utilize both ultraviolet and ionizing radiations for microbial control. And we use those a lot, more than you would think. And so we'll get into that in methods of control. And they work differently. The ionizing radiation is a much more reliable way. Ultraviolet is useful, but not exceptionally useful. It's useful to, what you'll see is it's useful for keeping things from growing, but not killing things. Okay. It's a little bit different. And certainly certain things with pressures can be, and again, these are the unusual bacteria that we typically see in the archaea categories that are able to do this. Okay. And here they're talking about the idea of associations between both similar and dissimilar microbes. This is the whole thing of what we see more in slime layers and in these interrelationships between microbes that we're exploring much more now. So you'll see some of the examples. Pardon me. And they're going to talk about the interactions and ones that are obligatory and non-obligatory. And a lot of them are very much nutritional. I mean, these are it's not like, oh, I want to live there. They live there because, they can live there because they have adequate food supplies or adequate conditions. I mean, there's not a conscious decision. Oh, I like it over here. They're not. And so the general term we give for interrelationships between any living things are symbiotic relationships. So symbiotes, and this is a consistent thing that we see, and I have a very difficult time between these first two. Okay, so mutualism, organisms live in an obligatory but mutually beneficial relationship versus commensalism. The partner called the commensal receives benefits while the other partner is either harmed or benefited. It's a very fine distinction, and I've seen that a lot. I mean, that where a lot of authors have commented about that. I don't see a difference. To me, nobody's getting hurt. That's the big deal. And the big deal why, when we look at things that we consider, to be parasites, a relationship in which the host organism provides the parasitic microbe, think of it as an infection, with nutrients and a habitat, and the host, us, suffers. That's what a pathogen is. That's a disease-causing agent. It's harming you, and in doing so, it's the growth of that organism is facilitated, and whatever byproducts there are. So I don't know whether I got it this morning. Don't know why. So other things, antagonism, association between living species that errs when they compete. Okay, fine. So when we're going to look at antibiotics, okay, that's something we're going to get to relatively shortly. When we start to look at compounds made by someone, and we're actually going to talk about it today, some organisms, such as antibiotics, in the environment that inhibit or destroy the other microbe. So they're fighting with one another. And it's a competitive thing. It's not decision-making so much as it is just an interesting nuance about any living thing that's trying to survive in an adverse environment. It adapts. It begins to do certain things. So, again, whether the first microbe has a competitive advantage, I would buy that. Soil, mixed communities, for interrelationships that are mutually beneficial, we certainly have those. The classic example would be gum disease or cavities, okay, and even some bloodstream infections. Typically, they're the interactions. So we see that with dental tartar creating this interesting biofilm that facilitates the growth of certain organisms and also the conditions to facilitate karyogenic disease cavities that are there. And they'll go through that type of stuff. Okay, so it starts with one colonizing it, and then other microbes can attach to those organisms or to some of the substances that they've secreted, and then it grows and releases chemicals, et cetera, et cetera. And a variety of different things occur with regard to this sort of interesting synergistic environment, something we're really studying a lot of now, to be able to look at what those environments are doing microbially. Maybe another example would be gut bacteria, which is another interesting example where they're trying to deal with a variety of disease entities by altering, inherently changing people. And it's rather repugnant if you think of it. It's called fecal transplants, which I'm troubled by that. Just, just doesn't appeal to me. Though our dog could be a donor. He's a very willing participant in that. Which of following describes which organ is benefited and one is harmed in some way? That would be a parasite. Okay. Yeah, now we're coming to the big player here. This is the end of the chapter. Every book has it differently, some in the beginning, some at the end. This is about the bacterial growth curve. So effectively what happens is they've started to study bacteria in what's called a closed system. Now, what's unique about a closed system, it's what you're doing in a lab. It's a test tube. Okay, it's a plate. Bacteria have a limited amount of nutrients. You can't get rid of the waste products. So over time, it's going to change the environment. The more bacteria grow, effectively, it's going to alter the living conditions because they're going to use up the nutrients and the waste products are going to accumulate. That's different than what we call a continuous culture. Continuous culture is what they utilize when they're making antibiotics at a big pharmaceutical company. They're continuously adding nutrients and siphoning off waste products. So they're holding the bacteria at a certain position in what's called this curve in order to optimize production of whatever they're trying to get. That's kind of the way it works. So, and you hold it at different levels if you're trying to make antibiotics or if you're trying to do genetic engineering and make human insulin. That's the distinction in these two types of things. It all starts with this. It's binary fission. Bacteria divide in two. The cell gets bigger, hard to see because they're not that big to start. Chromosome duplicates. Basically, we start to see a separation and eventually they divide. Voila, this would see. Nothing special about this whatsoever. It's just multiplying in two. Really, it's not mitosis because that involves pairs of chromosomes. And that whole thing with all those different phases, prophase, metaphase, anaphase, telophase, cytokinesis. Not here. Just we keep dividing in two. Nothing to it. We look at the amount of time to complete this cycle from the parent cell to the, quote, two daughter cells. Okay? So, and as long as the environment is favorable, read that as sufficient amount of nutrients and not an accumulation of waste products, it will continue at that rate. Typically, most bacteria, the ones you're using in the lab, every 20 to 30 minutes, they duplicate. So if you have one that does it every 20 minutes, in a matter of 3 hours, they will have doubled 9 times. So the formula, such as it is, and I used to have students do the math, there was a revolt about 20 years ago. So I stopped doing that. I don't know why. I guess it was those threatening letters I got. So basically, whatever the starting number was, call it, X. And I shouldn't call it X, it's confusing when you're putting a time sign. So let's call it Y times 2 and then to the n. What that n is the amount of doubling it does. So again, it's 3 hours, and it's every 20 minutes. That would be 2 to the 9th power. And it doesn't take long to get a big number. 2 to the 6th power, 64. 2 to the 7th, 128. You double it. Remember? Okay, 256, 512. So if you started with 1,000, now you got in a matter of 3 hours, you got 500,000. That's a lot of bacteria in a very short period of time. That's why those plates and those cultures that you make grow so rapidly in the incubator. You don't see it right away, but in a matter of a day, if you came back, and you come in once a week to see what's growing, but if you came back the next day, it's growing a lot. So here they summarize that. Average time 30 to 60 minutes, closer to 30, sometimes even shorter. The mycobacteriums, tuberculosis and leprosy, very long. That's what people don't, I mean, those are not diseases that occur right away. You need continuous, that's what we read from this, the idea of understanding that, how rapidly things can infect you. Okay, so certain environmental bacteria, terms in months. Most pathogens, disease causers, relatively short generation times. So here's what they're showing you. And really, if you can look at it this way in a linear type of curve, but this is a classic, what's called an exponential growth. So things can expand additively, things can expand geometrically, and things can expand exponentially. This is exponential growth. And exponential growth means it looks like it's growing fairly slowly, and all of a sudden it shoots off the chart. And that's what you're starting to see. You're starting with one, and in a matter of what, 6 generations, look what you've got, or 5 generations rather. Look how rapidly that expanded in a relatively short period of time. That's the critical idea. So here is this, n times 2 to the n, blah, 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 blah. It's like I was writing up there. And so that's why you develop the number. Whatever you start with times the number of generations, calculate the number of generations. It's like if you had a penny and every day you doubled it, within a month, you'd have an immense amount of money. Okay, it doesn't take long. If only I could do that. So, too many expenses. So, the growth curve, very predictable pattern, closed system. So, how it's done is you basically, what they did was they took a fixed number of bacteria and they inoculated a tube. And then what they would do is they take a sample and look under a microscope and count the colonies over time at intervals. So they incubated the tube, sampled it, plated it out. They do what's called counts. Something you may or may not do those in your lab. It depends on what your instructors want to do and how thorough the lab is. We have a lot of labs and a comparatively limited amount of resources. So you can't do all of these types of things. But this is when you start doing colony counts are important. You'll see that if you're going to work in a hospital when you have somebody with a urinary tract infection. A lot of times it's not enough to see bacteria in the urine because they're relatively common. Okay. Depending on how the urine sample was obtained, there's things called a clean catch and not a clean catch, those kinds of things. But what happens is then you do a colony count to see how, not that is there bacteria, but how many that are there. And that's done by doing a colony count. And what you do is you serially dilute the urine, let's say, until such, and then as you begin to reduce, and that's where you hear things like parts per billion and parts per trillion, which you're able to actually do a count to find out. And we look at countable numbers for those kinds of things. So effectively, that's the strategy. So here you start with it. So every hour, roughly, they're doing a count, and you're beginning to see the amounts of organisms that are there. And you can judge it by different things, but the best way to do it is to plate it out and to really count the colonies, or to dilute and count the colonies. So I'll go over and show you the curve, and then we'll backtrack. This is the curve. This is a consistent finding. What they're showing you in the tube is that the color changes in the tube are where we really don't see any cells, when we begin to see live cells, when we begin to see dead cells, etc., like that. So it's a very consistent kind of a curve. We'll get back to it. It all starts with something called lag phase. That's the phase between when it starts to grow and we can actually begin to observe growth. And this is, you're going to love this, this is a logarithmic graph. Anybody familiar with logarithmic graph paper? See, you were born in an age of graphing calculators. What was that T83 or whatever it is? Something like that I had to get for my kids and spend ridiculous amounts of money, though they would never use them. Okay. It's all right. My younger two, their math level is addition and subtraction. And my oldest, although he's a captain of a destroyer, his probably is not a whole lot more advanced. Never spent a day in a science lab. Never. And all those things he has to control. Go figure. But I digress. Are you interested in science? No. His degree from Duquesne, political science. That's as close as you get to science. Oh, where did I go wrong? But what we used to use was logarithmic graph paper. That way, I mean, you've got an x-axis. The y-axis is in terms of 10 to the power. So rather than going from 0 to 10, this is going for, 100, 10,000, million, 100 million. We're at 10 billion at that point. So you're able to graph large numbers and make sense out of them. So it's almost like how fast it's accelerating would be the way to describe it, as opposed if you're thinking of in terms of velocity versus acceleration. So you'll be able to graph that. That's what with logarithmic graph paper. The logarithms are the basis for the original computers, if you did not know. Years ago, we had an interesting tool called the slide rule. No, not ringing a bell, is it? Where have you been? Oh, I got to do this. You're just awful. You're terrible. Never heard of it. Oh, God. That got me so excited. Slide rule. Here, this is a slide rule. You could even buy one. I'll bet you get one at Amazon. And that's how we didn't have calculators in class. We had slide rules. That was how we did calculations. And it was all based on 10 to the power. They didn't have calculators. The first calculator that I used in college was 1972 or 73. And it was chained. It was about this was like biggest like a phone. And it was chained to the wall because they were afraid somebody would steal it. And your phone now does so many more things than that ever could do. Just say. See, look, $9.99 on eBay. Engineering drafting tool from the 60s. Go ahead. Say one word and you're in trouble. Okay, back to logarithmic graph paper. Oh, terrible. So the whole idea is we're able to look at not only the vast number changes, but get an idea of how rapidly they're changing. And it's just like any slope of a curve. The closer it gets to vertical, the faster it's going. So that's another factor to look at. So the lag phase is like the getting to know you phase. When you put an organism in a new environment, what does it start to do? It doesn't start to grow right away. It begins to assimilate into the environment. It begins to absorb nutrients. It sets the framework for reproduction. Once it starts to reproduce, it goes very rapidly. If it does reproduce, it's such a small amount that when you sample it, you can't see it. So the lag phase is usually a couple of hours before we observe changes. Then once it starts to grow, watch out. As long as there are adequate nutrients and not an accumulation of waste products, it will grow relentlessly until such a time as we begin to see a change in the environment. That change in the environment is highlighted by a lack of nutrients and accumulation of waste products. And basically what's happening, the space is being occupied tremendously. That's there. So you're running out of things to eat. You're running out of places to throw away the garbage. And there's a ton of you in there. And what happens is it's erroneously, sometimes you'll see this drawn like this. Okay? Now, living systems don't make sharp turns. Gradual changes. The conditions didn't all of a sudden become intolerable. So years ago, we used to refer to this as, because when it starts to grow unrelentlessly, we call it log phase, which is for logarithmic or exponential growth. And so they used to call this late log phase. That signaled when conditions were changing. And by the same token, then it would enter stationary phase. And people thought, well, it's not growing at all. That's not true. What happens is as many organisms are growing as are dying. By this time, they have run out of nutrients. So what do they eat? They eat the dead organisms that are there. Organisms, once they die, bacteria in a population effectively explode, and their contents become the fuel for the ones that are surviving. So only the hardiest, the strongest, are able to survive. And that's a consistent truth when we see in evolutionary curves. Various kinds of adaptations that facilitate being able to stay in harsh environmental conditions are the ones that are favored with regard to the theory of evolution. Okay? And so in stationary phase, even though it appears that they're not growing, they are. It's just as many are growing as are dying. And eventually the conditions become so adverse that we enter something called death phase, when more are dying than are surviving, and it's not nearly as fast as exponential phase. That's what you see. And even there's a prolonged decline phase where some cells remain dormant, and you theoretically you could plate them out and under the right conditions get them started again, theoretically. But there's some very interesting nuances with this, and I'll get as the nuances that are so important when we begin to look at how we generate things in the laboratory. So I'll get here and I'll backtrack and get back to their discussion of what it is. So the lag phase, newly inoculated cells, period of adjustment, enlargement, synthesis. They're not multiplying at a really large rate. You really can't see them, and they're sparse. So it's very, very difficult to see. Once they enter a log phase, that it's not geometrically, it's exponentially. The curve looks geometric, but it's exponential. Will continue as long as the cells have adequate nutrients and the environment is favorable. What do we see? Two things that are there. When we have, and this is really the take-home point of understanding this curve. Point one, log phase is absolutely the best time to attack those bacteria. It's the best time to treat, assuming it's an infection of significance, best time to treat. Why? Because those cells are gobbling up everything in their environment. So when you add an antibiotic, all they're doing is growing. So all they want to do is eat whatever in the environment. If you put an antibiotic in there, it's a killer, it's a poison to them, they're going to gobble it up, a la a ravenous dog. That's the whole. My dog is not so much. He's free. We had him sequestered so he wouldn't interact with the cats. And we finally removed the barriers after a year. So we had to run to the house. He was in there. When you go upstairs, follow you around. Get the whole house, fix the floor. Oh, so. Thanks. You trust me. No. We'll watch it. So that's the best time to treat the infection. That's the whole idea of the treating, identifying and treating things early, because they are the most susceptible to treatment at that point in time. Because all they're doing is growing. They haven't really developed defenses for adversity. The other factor, they produce a metabolite, a waste product. We call it a primary metabolite. The beauty of primary metabolites is that's where we find useful stuff. When we utilize bacteria, if we genetically engineer, that's where we'll find the insulin or the human growth hormone that we've engineered. If there's a particular substance we're trying to obtain from a bacteria, whether by genetic engineering or not, that's where we find it. Now, what happens next? We see that change. The division rate slows down, depleted nutrients and oxygen, organic acids, biochemical pollutants, whatever you want to call them, waste products, bad stuff. So the birth and death rates are equal. We see a fundamental change, and there are two of them that occur there. And that makes it more difficult to treat. So when we get to effectively stationary phase, it starts in what's called late log. We see a change. We see secondary metabolites because you don't make the same stuff when the conditions are adverse. What do some bacteria produce then? Antibiotics. So when we want to harvest antibiotics from organisms, in a laboratory or in a pharmaceutical company, we hold them in stationary phase. Number two, ones that can form endospores, that's where we see it. So that's why in lab, I like to do endospore staining from plates that are old, because they've really gotten into a phase where I'm more likely to see endospores rather than from a tube, because they're still more in log phase than in stationary phase. So endospore formation is something that occurs with signs of adversity, limited nutrients, accumulation of waste products, etc. So that's a significant factor. And then, even though they don't die as rapidly as they grow, eventually the conditions are just overwhelming. Okay, depends on the resistance of the species, how toxic it is, slower than exponential growth phase. And then the so-called, we call it prolonged decline, they're calling it viable, non-culturable state. It's sort of a state of dormancy that even exists in relatively old cultures that are there, and not terribly important for us at this point in time. We see this, what this mirrors is the competition in living systems. What's different when they're invading us is we're an abundance of nutrients and a lot of room to make waste products. That's one of the problems that are there. So we are not a closed system. We're effectively an open system. So it doesn't mirror it exactly, but we use it to study it. And there's that curve. So population exhibit phases of rapid growth, slow growth, and death. Microbes in exponential growth phase are more vulnerable, antimicrobial and heat. I had so many diabetic patients who were so prone to infection. Call me anytime. My answering service will find me. This was a different world when I was in practice at that point in time. I would go in the middle of the night. Would you meet somebody in the emergency room, or you meet somebody in the office? If they have a diabetic with infection, I want to know about it now. Because the sooner I treat it, the better chance that person has to survive. The better person, they're going to have a good outcome. It's just the way it is. Cells in growth phase are more vulnerable to conditions that disrupt cell metabolism and body. That's what I mean. They're more susceptible because they're uptaking more of whatever the treatment is. Okay, are more vulnerable in general to inhibition and to destruction. That's really the take-home areas that I think are associated with this. So this is what you're going to see in the lab. Maybe you've seen it already. Did you inoculate tubes that turn cloudy or murky in the lab? When you do, that is a sign of growth. On a plate, when you see a little dot that's a colony, that means there's approximately 1 million organisms. If you have a tube that's clear and all of a sudden it becomes turbid or cloudy, and we measure it by turbidometry, okay, it has 10 million organisms that are there. The more turbid it is, the cloudier, the murkier, the larger the amount of population. You can determine that by utilizing a spectrometer, which I'm sure they'll show you here. So we have these. I haven't used them in a while in the lab. I've used them before in the lab. So here it's clear, relatively speaking, or low turbidity. You can see through it. There's either nothing growing in it, there's not enough to be significant, because you can transmit the light through it, versus being very turbid or murky, whatever you want to call it. And so the amount of transmission is very limited, and we can standardize that. And indeed, that's what they do when you begin to test for various antibiotic sensitivity, something you're going to do probably in the lab called the Kirby-Bauer test, which every hospital in the world does. So if you ever wanted to understand how they determine what antibiotic to use, you don't do it. It's not like, sometimes you make a good guess. But when you have an antibiotic that you need to be very specific, you have to have testing. It's called culture and sensitivity. So you take a sample of the drainage, you take a sample of the wound, a sample of the blood, the urine, the mucus, whatever. Okay, and you analyze it in the laboratory, and you have these little discs, paper discs that are impregnated with antibiotic, and you determine whether or not they will affect the growth or not affect the growth. And it's very much and we'll go over that a bit when we start to do our antibiotics chapter, but you probably will have seen that in lab by that time already. So this is something, this is still employed in laboratories because you have to standardize things to get the appropriate antibiotic dose. And they use, it's called McLaren's test. Don't quote me on that. Can't remember all these things. Other things, cell counts. Years ago, they used to do this with a slide that had little compartments in it. They used to do blood counts with that same thing as well. They had special slides that did before the age of automation. So here you can electronically scan them. This was typically done, Coulter counters. You can flow and how much it deflects light or electrical current. Obviously, you can use more advanced techniques to look at bacteria and different kinds. These are more expensive and not typically done. Anytime you start to use genetic testing like PCR or RFLP, which are techniques that you may or may not become familiar with. I mean, they're tests that we order all the time. If you want to see if someone has a particular virus or a particular bacteria, you do that test. You want to see genetically if it's in their bloodstream. Like I had to start a medicine for my arthritis, so it's an immunosuppressant, so I can't have tuberculosis. So I had to go out and get it. I knew I didn't have tuberculosis, but my doctor had to have a positive TB. You see it on TV all the time. If you ever had TB before, that all those disclaimers, that fast talking guy at the end. It's like the guy who used to do the alphabet on Sesame Street real fast. You know what I'm talking about? One of those fast talkers. ABCD, that type of thing. I forget who that guy was, but he was great. I think it was, it might have been, I don't know if Dan Castellaneta did. That's the guy who plays Homer Simpson, the voice of. Oh. See, there's a slide. Yeah. I see bacteria, little. We should do that for blood cells as well. Coulter counters, See you later. I think we got it. By George, I think we've got it. Now, you give me the opportunity to introduce the next chapter. You can have on Etsy $40. That's an expensive slide rule. Like when I was in college, people would see that was nerd equipment. Pocket protector, bow tie, suspenders. I have that outfit. Okay, and you'd have like a little, like a thing, like they have. You ever see these guys with the phone? They have in their slide rule thing, like a slide rule holster. Really? You're all looking like, what is he talking about? It's 50 years ago. What do you expect? Technology wasn't there. Moving on. All right. I did not put in, unfortunately, I erred and did not put in the PowerPoint on your Blackboard. I will do that this afternoon, sometime before we meet again. From this particular, I think it's chapter 5. Don't quote me on it. From this particular textbook. This is basically I've outlined it based on there's a certain amount of terminology. This is where we talk about sterile. This is a very clinically oriented chapter. By the way, we have concluded the information on the first exam, and yes, I'll do a dictation. Sadie's nagging me already about that. Thank you. No offense. Okay. So all of those things, disinfection, antiseptics, herbicides, all these terms that are there, where we use them, why we use different types for different types of materials, the type of things that are hard to get rid of, like endospores or mycobacterium like tuberculosis or leprosy, and ones that are fairly easy to get rid of, like generic bacteria, are typically easy. Different, and so there's quite a bit there. The terminology for sterilization, as you can see. So I took a little bit of time, and there's a lot of this information is important. There's a bunch that's there. So please look at that. And so that I did add to the Blackboard on week 2. I do it like exam 1, and this is like exam 2 starts with this material. So just so you're familiar with it. And since I didn't load the PowerPoint, I will just use the older PowerPoint, which I had handy. The other one, and kind of go through it. So this is from the Nestor textbook we use for forever here, and I've used more than any other. And this is one of those guys we talked about, Lister. So you can see he had a good long life, 85 or so. Okay. And so the whole idea of what we call him the father of modern aseptic technique or antiseptic technique. So he was thinking about it and he used this is an agent that's interestingly enough been used for a very, very long time and more or less successfully in both topical products and various other compounds that were used. And I'll give you the history of it. And it was called, in the old days, it was called carbolic acid. It was really a cleaning solution. And phenol is something, if you did chemistry in the lab, you have something called an organic chemistry. You have aliphatics and aromatics. Aromatics because they smell. And yeah, phenol is a classic aromatic. So directly on the damaged tissues where it prevented infections. I mean, in very high concentrations, you can cauterize with it in a variety of things. And so he did it not only by treating the skin, using dilutions of it to wash hands, wash instruments, cleanse off. And this is when we talk about things like betadine. And they named the oral antiseptic Listerine, and that's a long time ago, 1879. We're talking about a better part of 150 years ago. Okay, when it was introduced as a surgical antiseptic. So it's interesting, topically. So this was the problem. Maybe into the turn of the last century, surgery was extraordinarily risky. You were very fortunate to be able to have a surgical procedure done without significant degrees of infection that were there. And we had no means, we didn't have antibiotics to deal with infections. Infections were a death sentence. Okay, we'll talk about my biological grandmother died in my dad's mom died in 1927. He was only 13 years old of a really a variation of a fairly common streptococcal infection called, those days it was called erysipelas. It's really it's sort of similar to, let's say, what would be scarlet fever. And today penicillin would clobbered if it was recognized right away. It's very interesting. So, I mean, if you want to go back into context about it, okay. So all of those things, they weren't cognizant about hand care. They weren't cognizant about the environment or airborne microbes. And obviously, it's all changed today. So you're going to see that many of you are going to work in clinical environments or at home. And if nothing else, if there was a benefit to COVID, it would be all became more cognizant of these kinds of things. They're there. And if there was such a benefit from having a disease entity, maybe it just made people a little bit more wary about that. So it brings us into, and this is a certain amount of definitions. Sterilization. What does it actually mean? Removal or destruction of all microorganisms and viruses. The definition of sterilization does not include prions. Okay. You might remember early on, prions are these interesting misfolded proteins, mad cow disease. We look at them more closely in terms of viruses because they're what are effectively considered an acellular form of, we call it an agent or an acellular form that's potentially a disease causer. We have, at this point, the reason it's not included in this definition, and it's nothing to be fearful of, is we really don't understand exactly how to get rid of them. There's been a lot of theories. When I first started teaching this more than 20 years ago, they thought it was, if you used similar to sterilization for like 4 hours at a higher temperature. Now now the articles, well, it's still higher temperature, but it's only 1 hour, which is again saying these three words: I don't know, or they don't know, that are there. So when you get something whose contents are guaranteed sterile, it has nothing to do with prions. So we do, and most of us feel that prions come probably more from ingestion than anything else, and less of a topical problem. More on that when we get to that area. So a sterile item is free of microbes, with the exception of the prions, and particularly endospores. Again, not including the prions. The endospores, as far as we know, of anything else, with bacteria, viruses, fungi, protozoan, et cetera, Endospores are the toughest to get rid of. If we get rid of them, everything else is gone. That's the idea. The other distinction is between these two processes, disinfection and antisepsis. They are not the same. Disinfection does elimination of most or all pathogens, but not all of them. And disinfection by implication involves inanimate objects, surfaces, tabletops, instruments, apparel, surgical masks, gloves. Okay, those are items that are, some of those can be sterilized, some cannot. But by definition, they are not living. You cannot sterilize living tissue. That's a process called antisepsis. And by definition, disinfectants are used on inanimate objects. Antiseptics are used on living tissue. If you want to sterilize living tissue, you have to make it dead tissue first, which is sort of counterproductive. So disinfectants, chemical used on inanimate objects. Another term we utilize are germicides, because in the old days, everything was a germ. And then you can subdivide that into bactericides, fungicides, and virucides. The side being killing, and obviously whatever the prefix is, tells you what it's addressing. The one that's significant for us in this discussion are called sporicides, because they can attack endospores. So things that are sporicidal have the potential, if used properly, to sterilize. It's somewhat of a fine line, but not entirely. Different things at different concentrations can be both antiseptics and disinfectants. And probably the classic example would be hydrogen peroxide, okay, which can sterilize at high heat and high concentrations, but is an antiseptic at lower heat and lower concentrations. Yeah. So there's and some of these in these textbooks are. I'm trying to give you what the clinical utilization is of things like that. So it's for instance, we're going to look at the difference between bleach, which is a halogen, periodic table over there, that row, fluoride, chloride, iodine. Remember that routine? It's all up there. Okay. It's a halogen. And iodine, betadine, most common used agent in a hospital environment, are in the same category, but they're not the same. Chlorine-based things are disinfectants, like Clorox, bleaches. Betadine, iodine-based things are antiseptics. It's just a difference. It depends how they're formulated, how they're utilized, etc., that are there. So those are important definitions. So what you should know is the definition of sterilization, removal or destruction of all microorganisms and viruses, including bacterial endospores. Disinfectants and antiseptics, disinfectants on inanimate objects, surfaces, etc. Antiseptics on living tissue. These terms, decontamination and sanitization, are terms that are not part of science. They are much more part of governmental bodies or regulating bodies. Who's to say something is decontaminated? It depends on, does the state say that? Does the federal government? Does the locality say that? Does the country say that? Okay, it reduces the number of pathogens to what that governing body calls a safe level. So, I mean, someone may tell you, oh, make sure that's decontaminated. Well, basically, you're cleaning it up. Okay. So it depends on exactly what you're decontaminating or what was the presumed to be the contaminant as to how you go about doing it. And the same is true for sanitization. It's substantially. What does that mean? By a factor of 10, by a factor of 100, by a factor of 1,000, 10,000, a million. And you'll see these numbers are real. Reduces the microbial population to meet accepted health standards. Well, who makes the health standards? Governing bodies. So what might be clean in your house you might look at somebody else's house. Oh, we just clean, and you go, oh my God. My office, for those who've been in my office, has that je ne sais quoi. We like to call it the lived-in look. Occupied. It's like we got a new chair in the house, so my dog could have his own chair. He's been stealing my chair, so we got it. Well, I got a new chair, and he's having that. All right, enough of that. We'll end here. We'll move on. Enjoy. Goodbye. Stopping recording.